Greetings. We will have some more discussion on the Levinson's theorem, which we already established in the previous class. We will also introduce the idea of effective range, which was introduced by Fermi and later Beatty in nuclear physics, and we will discuss some applications, especially in the domain of ultra cold atoms, especially Fermi mixtures, and so I will just make a little mention of some of these things, and we will conclude unit 1 and then come back to collision physics a little later in this course, because we need to get into second quantization and other things which I would like to begin in unit 2. In fact, unit 1 itself I wanted to wrap up a little earlier, but because of our energy and slow energy collisions and the Levinson's theorem, it got extended. But with today's class we will conclude unit 1. So essentially the Levinson's theorem we formulated for the S waves, the low energy limit of the phase shift of the scattering phase shift is either n pi or n plus half pi, and it is n pi typically, but it can also be n plus half pi if there is a resonant bound state solution which is in existence at that limit. So under those conditions you can have low energy bound state at 0 energy, but this will not be normalizable because this will be continuum state. Otherwise bound state energies, discrete energies are essentially square integrable. This is not. So the boundary condition is different, which is why it is called as a half bound state. And for L greater than 0, for either 1, 2 or any other value of L, the phase shift is always n pi for L greater than or equal to 1. The resonant value of the cross section, which we checked for the square well spherical potential, the cross section goes as 1 over k square, and the resonances occur whenever the strength of the potential is given by this parameter root u0a, or more commonly by its square, which is u0a square. And when this parameter root of u0a is equal to pi by 2 or 3 pi by 2, 5 pi by 2 and so on, that is when you get the resonances and the number of bound states increases. So the 0 of the phase shift is set with at infinity, that these phase shifts are measured with the phase shift at high energy limit. So this is the reference phase shift, and this reference is indicated over here, that delta L at 0 energy minus delta L at high energy limit, this is the difference which is given by n pi or n plus half pi, depending on whether L is 0 or 1, 2 and 3 and so on. So we discussed this table in our previous class for a square well potential, and notice that the potential can be made stronger either by making it deeper or by making it wider. And if the potential strength is indicated by this product beta times A, where beta is a measure of the depth of the potential and a measure of the range of the potential, then in this range the potential is attractive, but the number of bound state is 0. So just the fact that the potential is attractive does not guarantee that a bound state exists. So the potential has to be sufficiently strong to be able to bind a state, bind an electron in that. And as the strength parameter becomes pi by 2, that is when you get the first bound state, so that for all values of the strength which are greater than pi by 2, you have got one bound state, and this number remains the same till this strength parameter becomes 3 pi by 2, which is when you get the next bound state. So just the threshold of the bound state is what I have indicated by this asterisk. So asterisk is just when the bound state is picked up. Okay, for all values of the strength lower than that, you do not have the next bound state. and if you see the last column, the phase shift, it is either 0 or pi by 2 or pi or 3 pi by 2 or 2 pi, completely in accordance with the Levinson's theorem. So, what happens to the scattering length in this process? Now, that is indicated in this table, because the scattering length is given by this expression for the square well spherical potential, and this scattering length, it actually it is in this range. So, it is negative in this range, but the potential is not strong enough to bind an electron. So, the scattering length being negative is a necessary condition, but not a sufficient condition. It has to be negative, but it not only has to be negative, it has to be as negative as it can get. Okay, how negative can it get? It really has to go toward minus infinity. Okay, so you will see how that happens. So, here the scattering length is negative, this is alpha, this is the scattering length, this is negative in this range, and it becomes most negative when this beta A becomes pi by 2. It becomes in fact minus infinity, and then across pi by 2 it reverses the sign from minus infinity to plus infinity. It then becomes positive, and it is almost like a repulsive potential, because it cannot bind any more electron into the system, or any more particle, whatever be the particle. So, the scattering length has to change sign at this threshold, which happens at pi by 2, then it happens again at 3 pi by 2, when the scattering length again goes from minus infinity to plus infinity. So, I want you to pay attention to how the scattering length behaves and how it reverses the sign when it is about to, when the conditions of the potential are appropriate to pick up a bound state. So, this I will discuss further. So, a bound state gets formed when the sign of the scattering length is about to change. It must change from negative to positive, but it cannot jump from negative 10 units to positive 10 units. It has to get as negative as it can get. So, is minus 20 more negative than minus 10? Yes, it is. Is minus 100 more negative than minus 10? Yes, it is. What is the most negative number you can think of? Minus infinity. So, that is what has to happen. Okay. So, it has to be negative, only then you have an attractive kind of potential which has the capacity to bind a particle, but it not only has the scattering length not only has to be negative, it has to get as negative as it can. So, this is what happens. The phase shift is jumps through pi, so it picks the first bound state when this parameter is pi by 2, as I mentioned, right. So, at the value of pi by 2, which is 1.57, this is when the phase shift changes, it picks up a 1 bound state, and beyond this the phase shift is pi, because the phase shift is for S wave, I am considering only the S waves over here. So, the S wave phase shift at 0 energy is equal to pi times the number of bound states. So, now that there is a 1 bound state, the phase shift is pi over here, then beyond this value, which is 3 pi by 2, you get a phase shift of 2 pi, then the phase shift is 3 pi, and so on. So, it goes as a step function. Now, let us understand this idea. Look at the expression for the scattering wavelength. It is alpha is A, this is just a typical case, which is a square well spherical potential, which we are considering for the sake of simplicity, but the results are much more general than that. Now, for this, the scattering length is given by A times this factor 1 minus tan A beta by A beta. This expression we have already obtained in our previous class. Now, the question is, when does alpha get to be most negative? Yes, for alpha to be most negative, it is 1 minus this, right. So, this number, this ratio, which is the tan A beta by A beta, this must be greater than 1. that is the first condition, that is when alpha will go negative. But then when does it go most negative? When the tangent function becomes the largest. And when does that happen? When the angle becomes pi by 2, 3 pi by 2 and so on, right. So that is when the scattering phase shift is going to be such that you will be able to pick up one bound state at that stage. So that is when alpha is most negative. So you get the first bound state when this angle A beta is pi by 2, but it should be infinitesimally less than pi by 2, because it must be negative. Okay, it should be negative, but as negative, so tending to minus infinity. Okay. So this is when you get the first bound state. Okay. Now likewise you get the second bound state again when this tangent function goes to plus infinity. The tangent function will go to plus infinity at 3 pi by 2, okay, which is sin theta by cos theta. So this will go to infinity when cos theta goes to 0, and this will again go to infinity, and you will get the second bound state over here. Likewise you will get the third bound state when the angle becomes 5 pi by 2. Now let us ask, when does the scattering length become 0? At pi by 2 and 3 pi by 2 it goes to minus infinity. At pi by 2 it changes sign from minus infinity to plus infinity, because the tangent function jumps from plus infinity to minus infinity, right. When does alpha go to 0? Is it at the angle in between, which is pi? It will be slightly more than pi, right, because this ratio tangent theta to theta must be equal to 1. So it will go to 0 at a angles which is slightly more than pi. So let us say that that angle is pi plus epsilon, and at this angle pi plus epsilon the scattering length will change sign from plus to minus, and then between this value which is plus pi plus epsilon to 3 pi by 2 the scattering length will remain negative. Okay. So that is how the scattering length changes its sign according to this prescription, and here is a plot which shows you how the scattering length changes for an attractive potential as you increase the potential strength. So the potential strength, you have got this vertical line, on the right of this the potential strength is attractive, on the left of this it is repulsive. Okay. So it is some measure of the strength of the potential, and as you go toward right, more and more toward right, the potential becomes more and more strong, and it becomes capable of having more and more number of bound states as you go from left to right in this graph. Now if you see, the scattering length goes to 0 at pi plus epsilon over here. So this is not the center point between pi by 2 and 3 pi by 2, it is slightly off the center toward the right. The next time it will, the next 0 will not be exactly between 3 pi by 2 and 5 pi by 2, it will again be off the center toward the right, but not exactly the same value because theta has increased, okay, which is this angle A beta. So the tangent will have to be a slightly different value. So you will get that at a value of an angle which is slightly less than what it was in the previous case. So you will get 2 pi plus epsilon prime when epsilon prime is less than epsilon, so that it is slightly shifted. Okay. So these are not uniformly spaced zeros. So this is when the scattering length changes its sign, and this really has some very fascinating applications both in nuclear physics and atomic physics, because controlling the scattering length is a tool which is available to experimentalists, because they can have some external conditions with which they can fine tune the scattering length and have the potential either attractive or repulsive depending on how you tune it. So it gives the experimentalist a certain tunability on the physics and the kind of the experiment that he is going to perform. So, this is what we have, and when you have an attractive potential you only have the necessary condition. So, if you look at the necessary condition alone, you are not guaranteed that you are going to have a bound state or you are going to have the next bound state, because if you look at this region over here, this is the triangular region, it is not of course exactly a triangle, this is an arc, but if you look at this segment, the scattering length of course is negative over here, but it does not make the potential capable of having even a single bound state. Likewise, it is negative in this region also, which is in this shaded area. Okay. In this shaded area also the scattering length is negative, as you can see, but it does not give the potential a capacity to get the second bound state. To get the second bound state you have to hit 3 pi by 2, okay. And then you have another shaded area over here in which the scattering length is negative, but you do not get the third bound state. To get the third bound state you have to get to 5 pi by 2, okay, and only then you pick up an additional bound state. So, you have the first bound state at pi by 2, the second at 3 pi by 2 and the third at 5 pi by 2. Now, a positive scattering length is not when you can have a bound state at all. So, it has some similarity with a repulsive potential, because you just cannot have a bound state under those conditions. So, now let us look at the asymptotic solution for the S waves. Now, as r tends to infinity, your solution to the Schrodinger equation is this capital R. This little u is a function which is defined as little r times the capital R, which is the solution, right, and the solution, this solution is a sine wave, as we have seen. For L greater than 0, you know you have got a sinusoidal solution which is phase shifted by L pi by 2 plus a scattering phase shift which is delta, but for the S waves L is equal to 0. So, the solution in the asymptotic region r tending to infinity is a sinusoidal function with argument kr plus delta, where delta 0 is the S wave scattering phase shift, and we have seen how it behaves and how it is connected with the number of bound states through the Levinson theorem. Now, the low energy limit of this is obtained by taking the limit k tending to 0, because h cross square k square by 2m is the energy. So, this is the low energy limit, and I recapitulate the definition of the scattering length alpha, which is given by these relations, and this is the low energy limit of the scattering length, right. The tangent of this function is minus alpha times k. So, now if you look at the low energy limit of this function u, which is the radial function multiplied by the radial distance. So, this function u in the asymptotic region, when the scattering phase shifts are small, this will become kr, but this delta is the same as minus alpha k. So, you get almost a linear relationship between u and r. This is an equation to a straight line, as you can see, right, and you would expect it to be so, because if you look at the radial Schrodinger equation and write it in terms of the function u rather than the radial function r itself, okay, then you must satisfy this differential equation. In the limit k going to 0, this term k square drops out. So, you get only d2 by dr2 minus u, this is the potential operating on the function, equal to 0. This is the form of the Schrodinger equation or the reduced Schrodinger equation, and then for the asymptotic region r greater than a, outside this range the potential vanishes. So, the effective differential equation that you have to worry about is only the second derivative of u going to 0, okay, and if the second derivative is 0, the first derivative is a constant, okay, and if the first derivative is a constant, you have got a linear relationship which is u equal to mr plus c. So, you get a linear relationship. So, that is what you have over here, you get essentially a linear relationship, and you recognize that the scattering length, now you can assign a geometrical meaning to it. It is, if you compare it with the equation to the straight line, you find that it is essentially the intercept, right. So, this is the linear relationship that you get, and this is the geometrical meaning of the scattering length. So, if you here alpha is greater than 0. So, it is a positive quantity, which is what you have for a repulsive potential, as I mentioned earlier, and at r equal to 0, which is here, this function will need to be somewhat negative at minus mk alpha, right, whereas at r equal to alpha, which is here, okay, the function would go to 0. So, that is the geometrical asymptote behavior of the scattering wavelength, scattering length. Now, you have seen that the scattering length must be negative, but it does not guarantee that the bound state exists. So, here is a case of an attractive potential, this is u, and this is the 0 of the potential, this is below the 0. So, this is a negative potential, which is an attractive potential. So, you do have an attractive potential, the scattering length is negative, but not sufficiently negative to have a bound state. So, here the scattering length is negative, this is the 0 of the distance axis which runs from left to right. On the right of the 0 you have got positive distances, on the left of the 0 you have got negative distances. So, the scattering length is negative in this picture, as you can see, right, but it is finite. Look at this intercept, okay. You want the scattering length to become as negative as it can. So, this intercept has to go farther and farther and farther toward minus infinity, right, only then you are going to have the bound state. So, that is what you get when it goes farther and farther, this asymptotic line becomes parallel to this line, because parallel lines, they told me, meet at infinity. I have never verified it, but I think they do, okay. So, this parallel line, this asymptote, it will meet at infinity, and that is the negative maximum scattering length that you can get, and that is when you get the first bound state, and okay, that is when you have the 0 energy resonance, okay, that is the half bound state that we are referring to. And then of course, when the potential becomes a little bit stronger, so here this is the potential, you see that it has become a little stronger than what it was in the previous diagram, and in the next diagram we make it even more stronger. So, you see that it is a little deeper now, and now the scattering length, just because it has become deeper does not mean that it will automatically pick the next bound state, because the scattering length has now become positive, and in fact you will not get a bound state under these conditions. You will get a bound state only when the scattering length again becomes negative, and not merely negative, but the most negative that it can get. So, those are the conditions that are necessary to pick an additional bound state, and what where the scattering length find lots of applications is the fact that it gives you important idea about the physics of the collision process without having to look at the detailed structure of the potential. Like in the previous diagram, we had this potential which is an attractive potential, but the shape of the potential is not something like a square well. But the general results of our discussion remain equally valid for this case as well. We have demonstrated it for a square well potential, but it is valid for potentials having other forms also, and the actual detailed structure of the potential is not necessary to be seen, and this is a case similar to how you will look at a charge distribution. So, if you are looking at a charge distribution, there are some positive charges and some negative charges. So, let us say the red are positive charges, then black are the negative charges. They may have some random shapes, okay, they may be diffuse, they may be point charges, it does not matter. So, the details of this picture are not really important, but you may, let us say that you have got various charge distributions, positive and negative. Now, the question is, where are you observing this charge distribution from? Are you observing it from a point that is close enough? Okay. It is only a coincidence this observer looks like Newton. Okay. And if he is close enough, he will see a very complicated charge distribution. Okay. He will see monopoles, dipoles, quadrupoles, octopoles, infinite, right. But if he goes far away, he will see that, okay, everything is packed together and there is a single charge at a single point, and the details of the structure or of the potential that we are talking about in the case of collisions. So, those details do not become relevant, and they can be, the effect of that can be parametrized, which is what the scattering length does for us. And how does it do it? Because when you are dealing with slow collisions, if you look at the de Broglie wavelength, because the energies are small, the velocities are small, and the velocities being small, the wavelength is large. And if a wavelength is really large, it is not going to see the details of a small structure, okay, because to see something that is really tiny, you need very short wavelength. So, this is a large wavelength and you are not going to see any details, and the essential focus in S wave scattering at low energies, which is the domain of slow collisions that we are discussing in this unit here, all the essential properties are contained in the symmetry, which is the S wave, and then it is contained in a parameter which is the scattering length, which is alpha. So, we now introduce what is called as the effective range. So, we again go back to the square well potential, because it is very easy to define it for a square well potential, and this formalism was developed by Fermi and Beatty and so on. So, the main formulation that we follow is due to Hans Bethe, which came out in a paper in PhysRev in 1949, and this was studied in the context of nuclear physics, in the context of 2 nucleon scattering, neutron proton scattering, and and it was found from these studies that these interactions actually depend on the spin state. So, that was a major outcome of these studies, and in atomic physics it now has very fascinating applications in getting very cold atoms and BCS or BEC kind of systems by controlling the scattering lengths in the low energy domain. So, let me give you some brief introduction to this, although the subject is quite vast. So, if you have a Bose, if atoms are bosonic, you can of course seek Bose-Einstein condensation, because that is the premise which Bose-Einstein statistics gives you, that there is no stopping, there is nothing like a Pauli barrier which prevents identical particles from condensing it into one state, which is what is achieved if you have particles with integral spins. If you have bosons, there is no such barrier, the Pauli barrier or the Fermi-Dirac barrier. So, there are Fermi-Dirac particles for which you cannot do it, but for bosons you can get Bose-Einstein condensation, and this of course, as all of you are well aware, has been achieved, and there is a lot of excitement in atomic physics because of the Bose-Einstein condensates of atoms. Now, if your atoms are not bosons, but they are fermions, you can have Fermi atoms, you do have Fermi atoms, right, that depends on the total number of nucleons the atom has. So, now if you have fermionic atoms, you cool them, and then you can have 2 kinds of situations. One is that you can have a pairing like the BCS pair as you have in a Cooper pair, or you can have a bound state molecule, and whether or not you have a bound state depends on how you control the scattering length. So, you can have a BEC kind of pair, or you can have a Cooper pair. So, you have 2 possibilities over here. So, if you have a single component Fermi gas, atoms which are Fermi gases, and you consider low energy scattering. So, the only scattering which is of important at low energies, and why low energies, that is what cold atoms are, because the speeds are very small. Okay. So, the only scattering which is of importance in low energy at low speeds at low temperatures, you have got low speeds, and the only scattering which is of importance is the S wave scattering, which is what we have been discussing, right. So, in the case of S wave scattering, because of the Pauli exclusion principle, scattering is inhibited because the exchange interaction will tend to keep them apart, okay. And then evaporative cooling will not be achieved, but you can always achieve it by having some mixtures of these Fermi atoms with other atoms like Bose atoms, okay. So, you can have a Bose Fermi mixture, and then you can achieve, this is sometimes called as sympathetic cooling. What you do is you evaporate Bose atoms, okay, because evaporative cooling requires this collision kind of thing. So, you can evaporate the Bose atoms, and through the collisions between the Bose atoms and the Fermi atoms you can effect further cooling. So, that is one thing that can be done, but then what is of importance in the context of the discussion we are having is that you can control the scattering length. Now, we have already discussed that the scattering length is positive for repulsive interactions and negative for attractive interactions. So, in the case of Fermi mixtures, Fermi to get Bose-Einstein condensation of Fermi atoms, if you look at the energy diagram, then you can have two atoms with parallel spins. This is how they are in unbound state. So, you have got two atoms which are not bound to each other. When they get bound to each other, you get a molecule, right. So, that is a bound state. When they are not bound, they are unbound, and that is when they are free, and you have parallel spins between them, but then you can get a bound state whose energy diagram is given by this blue line. So, this is the interatomic distance, okay. And the interatomic distance, if you look at this diagram, you can see that as they get closer, if you can get the spin of one of these to flip, because the molecular bound state requires S equal to 0. If you can get the spin to flip, okay, then you can get a bound state which will have a lower energy than this. So, you can effect a transition from one kind of pairing to another kind of pairing by controlling the spin orientation. And how can you do that? Using a magnetic field, okay. So, you can use the magnetic field as a switch, and you can effect a transition from the unbound state to the bound state. Now, this is a resonance effect. Now, this will remind you of, at least those of you who have looked into the autoionization resonances or the Fano resonances as we sometimes call them. What do you have in it? You have got a transition, you have got two states which are degenerate. You have got a possible bound to bound transition, and you also have a possible bound to continuum transition. Now, the bound to bound and the bound to continuum, these can be degenerate, and when they are degenerate you have a resonance, that is the Fano resonance, or in the context of scattering theory it is called as a Fano-Feshbach resonance. So, here you have a similar situation, you have got a bound state of these two atoms, or you can have an unbound state of these two atoms, but in the unbound state you have got parallel spins, in the bound state you have got anti-parallel spins, and in this case you can have, when they are unbound, you can have a Cooper pair kind of pairing between those two atoms, and you can still have a Cooper pair. So, this is called as a BCS pairing, but then if you get bound molecular states of these two atoms, then you actually have a boson, and you can induce it by using some other cooling techniques into the Bose-Einstein condensate phase. So, that can be achieved by controlling the scattering length. So, these are the Fano-Feshbach resonances as they are called, and if you see, what you are essentially doing is controlling the scattering length by this magnetic field. So, as you can change the magnetic field, you change the scattering length, it is greater than 0 on one side, it is less than 0 on the other, and this is where you have the BCS and BEC kind of transition between the kind of pairs that the two Fermi atoms can make. So, this has got very fascinating applications in atomic physics, in the physics of cold atoms and Bose-Einstein condensation of Fermi gas atoms. So, in between, of course, the scattering length diverges, and this is where you have got a, this is what you call as a closed channel, and this is an open channel. So, it is very similar to what you have in the Fano autoionization resonances, where you have open channels and closed channels, and you can have a BEC molecular bound state of the two fermion atoms, but otherwise you can certainly have a Cooper pair kind of BCS phase. So, that brings us to the effective range formulation of Beatty, and I once again take the case of the square well potential, because it is very easy to illustrate it for this particular case, and we consider solutions to the differential equation for the function u, which is little r times the solution to the Schrodinger equation itself, and I consider solutions at two energies, one at energy E1, which is h cross square k1 square by 2m, and the other at E2, which is h cross square k2 square by 2m. So, these are the two energies that I consider for this discussion. Now, both u1 and u2 satisfy the differential equation. So, these are the two equations satisfied by u1 and u2 respectively. You can multiply the first equation by u2 and the second equation by u1, which is what gives you these two equations, right, and then you can subtract the second equation from the first. So, this is a very simple manipulation that I am doing, and having done this subtraction, you integrate every term from 0 to r. Okay, what is capital R? Does not matter, it is some value. Okay? It is of course not the radial function, it is a certain distance up to which you are carrying out this integration. So, carry out this integration and you carry out term by term. So, the integration of u double prime will give you these two terms, integration of this will give you these two terms, and you have to take the differences at the upper value, little r equal to capital R and little r equal to 0, because you are carrying out this integration from 0 to r. Now, you have this difference from 0 to r. Okay. So, we keep the value capital R as long as we need it, and finally, we will get rid of it. So, this is the difference of this product u2 u1 prime at upper value of r and the lower value of r. So, you must take that difference, and this for u2 u1 prime from the first term, and here you get a similar term from the second term, which is u1 u2 prime, and this difference must be equal to, I take this term to the right hand side. So, instead of k1 square minus k2 square, it becomes k2 square minus k1 square. So, look at the integral on the right hand side. If in that right hand side, if the value of r happened to be infinity, you would really have an orthogonality integral between u1 and u2. Okay. So, now we already know that these functions, both u1 and u2, these are solutions to the Schrodinger equation. Actually, this times little r is the solution to the Schrodinger equation, right. So, at r equal to 0, these must be 0, right. So, which means that the only value which is of importance is the value at uppercase r. but the quantities that we are looking at will not depend on this. So, that is yet to come. So, now we have gotten rid of the values of these factors at r equal to 0. So, this is the expression that we get, okay, right. This is what we have. Now, we define two functions, these are psi 1 and psi 2. This is not the solution to the Schrodinger equation psi that we started out with. These are two new functions that I have defined, and how are they defined? They are defined to be such that they are exactly equal to the asymptotic behavior of the functions u, and that is known, because the asymptotic behavior of the function u is that it is a sinusoidal function, the argument is kr plus the scattering phase shift. So, that is known. So, these describe the asymptotic functions. So, that is the definition of psi 1 and psi 2. So, these two functions are defined, and I choose the normalization as 1 over sine delta. The reason I choose this normalization is because if you look at this function psi and find its value at r equal to 0, then put r equal to 0 over here, this will become 0, and then you get sine delta over sine delta. So, you will get essentially unit normalization at r equal to 0. Okay. So, the normalization is chosen so that you get unit normalization at r equal to 0. So, the size is fixed. So, now the normalization is fixed. Now, this is our expression here with u1 and u2 both at r equal to 0 to be equal to 0. Now, the only value which is of importance is the value at upper limit r, and you have got an exactly similar expression for psi, because psi's after all by definition give you the asymptotic form for the same functions which already are solutions to the Schrodinger equation. So, you will get an exactly similar relationship. So, you have got two relations now, one is u, the other is psi. Notice the similarity between the two, but notice also the differences between the two. These are coming from the solution to our equation, right, for our potential problem. It includes the scattering phase shift. This is defined to be equal to the functions with respect to the asymptotic behavior r tending to infinity. So, that is the definition of psi. Now, having defined them, this is a very smart way of defining the function psi, because now you can just carry out, expand this term. So, you take the difference between psi 2 psi 1 prime at the upper limit r and the lower limit 0. So, this is the limit at the lower limit, this is the value of this term at the upper limit, and this is the value at the lower limit. But then at the lower limit at r equal to 0, you have chosen the normalization. So, you know what is psi 1 of 0, that is 1, right, that is how you chose the normalization. So, having chosen the normalization like that, you get this factor psi 2 0 and psi 1 0 are both equal to 1. So, you get this difference here. So, instead of this product you get only one of them, the other is equal to 1, and now I have these equations which I have numbered, because what I am going to do is to subtract from this equation 2 equation 6. So, let me write equation 2 and 6 once again at the top of the next slide and subtract equation 6 from equation 2. So, let us do that. Now, let us carry out a subtraction. Now, how was this defined? Now, this is some large value, it does not matter what it is, okay. Its actual value is not important, but we know that it is a large value, and because it is large, in this region, in the asymptotic region, psi and u are the same, because that is how you define psi. You chose psi to be such that they agreed with the asymptotic forms of the functions u, which means that these two terms cancel each other. Okay? When you subtract equation 6 from equation 2, this will cancel each other, and now you have only this term equal to the difference of the right hand sides. The difference of the left hand side amounts only to this term, and the difference of the right hand sides you must consider. So, this is the difference of the left hand side, there is a minus sign over here. So, I have now written it as psi 2 prime minus psi 1 prime at r equal to 0, and this is equal to k 2 square minus k 1 square integral 0 to r of this difference psi 1 psi 2 minus u 1 u 2. This is integrated from 0 to r. Now, we already know what psi 1 and psi 2 are, these functions have been strictly defined. So, you can evaluate their derivatives automatically give you the cotangent function times the inverse wavelength k 1, right, because this is just the original function being this, the derivative is k cos this theta divided by sin theta. So, you get these two terms, and you can put these two on the left hand side, and you get k 2 cotangent of the phase shift at energy 2 minus k 1 times the cotangent of the phase shift at energy 1 on the left hand side, and on the right hand side you get this difference times this integral from 0 to r. Now, there is no approximation so far. Now, take the limit r going to infinity, and if you do that, you will convince yourself that what you chose your r to be really did not matter, because we are interested in the limit r going to infinity. Okay? So, take the limit r going to infinity. So, now the upper limit I have written as infinity over here, and it is the same expression as I had on the previous slide, with the difference that the upper limit is now put at infinity, r going to infinity. So, this integral which is from 0 to infinity, this we introduce a compact notation for this. This was done by Beatty in the context of nuclear physics, and this was the definition of half rho. Okay? This is still not the range of the, not the definition of the effective range, but it is getting there. So, this is defined as half rho. It depends on two energies, one is the energy k 1, the other is the energy k 2. Okay? So, the corresponding energies are h cross square k 1 square by 2 m and h cross square k 2 square by 2 m. So, those are the two energies with respect to which this half rho is defined as this integral, and in terms of this integral, k 2 cotangent phase shift is equal to this term will go to the right, which is k 1 cotangent of this phase shift plus k 2 square minus k 1 square times half of rho. Okay? Now, if you take the low energy limit for E1, you let E1 go to 0 or K1 go to 0, then k cot delta at k equal to K1 will give you the scattering length, right, it will give you the inverse of the scattering length minus 1 over alpha. So, you can put minus 1 over alpha by letting K1 go to 0, and now you do not have two k's to talk about, because one of them has gone to 0, you are taking the lower energy limit. So, other need not be called as the second k or k2, we will call it as k. Okay? So, k cot delta, the left hand side, which is now k cot delta, becomes equal to k1 cot delta, which is now minus 1 over alpha, plus k2 square minus k1 square. K1 square has gone to 0, so you are left with only k2 square, but k2 is now what you are calling as k square. So, you have got k square, and then you have got rho over 2. This depended on two energies E1 and E2, E1 has gone to 0 and the second is E. So, rho now is defined in terms of two energy parameters 0 and E, one is the 0 energy, the second is E. Now, this is your expression for half rho. Now I should caution you that our notation is slightly different from what Betti used in his paper. Our alpha is inverse of what he has used for alpha. He has used 1 over a for what we have used as alpha. So now let us ask ourselves, what is the difference between rho and u, the psi and u. Okay. U's are the original functions that we started working with, psi are the auxiliary functions that we defined such that they had the same asymptotic behavior as u's. So if psi and u differ at all, they differ from each other only where the potential is, because the asymptotic forms are the same by definition, by our choice. Okay. So they are different only in the range of the scattering potential, and that is the small r behavior, that is in the small r range. In the asymptotic region, as r tends to infinity, there is no difference between them. So they are different only in the small r region, and when you look at atomic properties in the small r region, whenever you look at any property in the small r region, all properties, atomic properties which depend on small r, they are independent of energy. To take an example, you have seen that the radial functions go as r to the power L as r tends to 0, right, that is the small r part. Now small r behavior is r to the power L. Is it the same for 2s? Is it the same for 3s? Is it the same for 10s? Is it the same for 2p, 3p, 10p, 100p? No matter what the energy is, the energy of 2p, 10p, 100p are different, but as r goes to 0, they all go as r to the power 1. All the d wave solutions will go as r to the power 2. Okay. So the small r behavior becomes independent of energy. The reason it happens is that as you go to small r behavior, this term overtakes, and at low energy, no matter how small the potential is, this term will be greater than k square. K square is energy, so k square becomes irrelevant. Okay, k square becomes irrelevant, and you have the short range atomic properties become independent of energy, and that means that this quantity that you have defined as an integral from 0 to infinity, and this integral was, the integrand had this factor, it had the difference between psi and u. Okay. But these two differ from each other only in the small r region, not in the asymptotic region. So what is being integrated? The integrand is made up of such terms which become independent of energy. So this energy parameter over here you can get rid of, because, and then this factor psi 0 at 0 energy times psi at energy E not equal to 0 becomes nearly, these two become nearly equal, and this becomes psi 0 square. Likewise the second term becomes u 0 square for the same reason. Okay, because they depend only on the small r behavior. So in the small r behavior, now you have got a quantity which does not depend on energy, and you now have the definition of the effective range of the potential, because it depends neither on the energy nor on the capital R, and because that is already taken care of, you have taken the limit r going to infinity. So this is what is called as the effective range of the potential, and in terms of this you can write this factor, because you have got this half rho. So the half rho has come here, and then you have got a k square behavior. Then of course there will be some corrections. The next order correction is of the order of k to the 4. Okay. So to the leading terms, the scattering length minus 1 over alpha, to this, if this is your approximation to the k cot delta, if you want to correct this with the next order in k, the next order in k is k square, and this gets scaled by half the effective range of the potential, and then of course you have further corrections of the order of k to the 4. So this is the typical formula which you employ in effective range calculations, and just to remind you that beta is alpha is inverse of ours, and that pretty much concludes our discussion on low energy collisions. Of course we want to discuss collisions at higher energies, the Bahn approximation and so on, and that is something we will do in a later unit. We will come back to collision physics after we do the next unit on second quantization. So this is more or less the important piece of this result, that you have got this k cot cotangent of this phase shift, which is given by -1 over alpha times 1 over alpha plus this effective range, half of effective range times k square. You can get the partial wave amplitude in terms of this, because you have got the phase shift over here, and you can get the scattering amplitude which goes as this. Okay, so these things can be carried out, worked out very easily, and from the scattering amplitude you can get the scattering cross section, which goes as 4 pi times 1 over k square plus k square cot square delta 0. You can also manipulate these terms a little further, because you can write these terms and write the cotangent function, the k cot delta, in terms of the scattering length and the effective range, as we have done in the previous expression, and you can rearrange these terms. You can see that you will get a 1 over alpha square, okay, and by cross multiplication you can bring that alpha square to the top, so that the expression for the scattering cross section will have 4 pi alpha square, and then it will be weighted by the remaining factors, and this is just a rearrangement of these terms through cross multiplication and so on. You can work this out rather easily, and you will find that the scattering cross section goes as 4 pi alpha square divided by these terms. Okay, so this is a rather straightforward manipulation of these terms, so I won't spend any time doing it, and that pretty much concludes our discussion for this unit. And essentially we have got the conditions under which you get the bound states, the first bound state, the second bound state, the third bound state. For the square well potential it is very easy to demonstrate. For other potentials it is a little more complex, but essentially the relationships go on similar lines. You have seen that it has got major applications in nuclear physics, in neutron proton scattering in particular, which was the genesis of all this formalism which was developed by Fermi, Bethe and so on, and now in the context of modern applications in atomic physics, these are of great importance in getting BCS and BEC pairs of Fermi atoms. Thank you.